Let me say a very good morning, or I think good afternoon or good evening to all of you wherever you are. I know that some of you are, I think, connecting from other parts of the world, but thank you all for making it to our symposium. This is our, I would like to call it our, I think, our concluding highlight of our webinar series that ECS Purdue chapter is hosting this semester. So we're very fortunate to have three distinguished speakers and panelists. You are going to hear from them today. I am Partha Mukherjee, and I'm a professor of mechanical engineering at Purdue University, and also I serve as a faculty advisor to this chapter. It's my great pleasure to welcome you all this morning in the US. So I have a couple of slides to say a few things to kickstart our this symposium. Can you, Sushmita, could you say if you see my
Yes.
slide? Okay. 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 Perfect.
It's not full screen mode.
Oh, can you see full screen? Okay,
no,
great.
it's fine. Yeah.
Okay, perfect. So thank you again and welcome everyone. My take on electrochemistry, I would say electrochemistry is everywhere these days. And for sure, electrochemistry is playing a critical role in the energy landscape. This particular energy flowchart is very, I'm very, very fond of this energy flowchart. I probably saw it everywhere in my class, in any seminar that I start with. But let me start off with it again. Certainly, this is an electrified world and a digitally connected world, right? And from this flowchart, I could say this electricity is probably the electrical energies, or electricity is the most useful form of energy. And if we really would like to have more and more, I think, energy storage or energy conversion, and also vehicle electrification, or electrification in aviation, or electrochemical synthesis into useful or chemical fuels, or innovation and manufacturing, I think electrochemistry is everywhere. That's my take here. And electrochemistry is also going to play a role in process improvement and efficiency, energy efficiency. And I believe I don't need to tell you that all of us are carrying at least 2 or 3 portable electronic devices, all are powered by a battery in that sense, lithium-ion batteries, right? So that's my take. Electrochemistry is everywhere, and it's going to play a major role in energy innovation, in manufacturing, innovation in the chemical industry and chemical fuels in space, like that. With that, we also know electrochemistry is equals to multidisciplinary. It's very interdisciplinary, okay? And this is a perfect example of that. 2019 Nobel Prize in Chemistry went to, 3 innovators, right? We have a physicist, a chemist, and an engineer, and they created a rechargeable world for the development of lithium-ion batteries. And with that note, electrochemistry can be fun too. So this is a quiz for the attendees, especially the students and researchers. Can you spot whoever you can? You can spot a distinguished speaker from today here. You can spot a Nobel laureate here. And hey, you can spot me as well. I had a little bit of more hair by then, but hey, I'm losing it. But there you go. With that note, I would say that welcome to today's symposium. And I'm very honored to have 3 distinguished speakers from different sectors, I would like to say that. And they're going to tell us about their journey and the research and how they see electrochemistry in their daily lives of innovation and research, okay? And all 3 of them have one common theme. They are all trained in chemistry or electrochemistry. So with that, I'll just briefly mention, we have 3 distinguished speakers. We have Professor Emmy Prieto, Professor of Chemistry from Colorado State University, and founder and CTO of Prieto Battery Incorporated. We have Dr. Lakshmi Krishnan, Senior Scientist of the Material Organization from GE Research. And we have Dr. Judy Jeevarajan, who is a Corporate Fellow and Research Director of Electrochemical Safety at Underwriters Laboratories. With that, welcome everyone. I'll stop here, hand it over to Sushmita for the formal introduction. Thank you. Sushmita, it's all yours. And please unmute yourself.
Yeah. Thank you so much, Professor Mukherjee, for a wonderful introduction. And hello, everyone. Welcome to our concluding symposium of Purdue ECS chapter Spring 21 Symposium series. So my name is Sushmita, and I'm currently serving as the president of this student chapter. So those of you who are joining us for the first time, so this is the current executive board we have. We have Professor Mukherjee as our lead faculty advisor. We have Professor Laskin as our co-faculty advisor. We have Navneet as our vice president. We have Hanoi as our secretary, Julia as our treasurer, and we have Devanjali as our communication director. So as part of our activity for the student chapter, we started a webinar series in last fall with speakers from national labs, academias, industries, and that webinar series was quite successful. So we continued with that webinar series in the spring semester as well. And the theme of our spring semester was Women in Electrochemical Sciences and in Engineering. So we had distinguished speakers from, again, all over the national labs, industries and academias and different places from different countries. I'm very happy to be a part of this webinar series like organized by the Purdue ECS student chapter on this, like focusing on the women in electrochemical sciences and engineering. So now without further ado, I will introduce our today's speaker. Our today's first speaker is Dr. Emmy Prieto. Dr. Prieto is a professor in the Department of Chemistry at Colorado State University and the founder and CTO of Prieto Battery Incorporation. In addition to her research in lithium-ion batteries, she has active projects developing nanoparticles ink for photovoltaics, light metal nanoparticles for hydrogen storage, and novel nanowire structure. Dr. Prieto is a native of Colombia and moved to the US when she was young. She earned her BA in chemistry and philosophy at Williams College. After that, she earned a PhD in inorganic chemistry from University of California, Berkeley. Her postdoctoral work was performed at Harvard University, where she measured the electronic properties of single molecules and nanoparticles. While at Harvard, she was named one of the first L'Oreal USA for Women in Science fellows. Professor Prieto founded Prieto Battery Incorporation in 2009 with the goal of commercializing a novel three-dimensional high power density safe lithium-ion battery made from aqueous-based electroplating buds. Her company's strategic partners are Intel Corporation and Stanley Black & Decker. In 2011, she was named the ExxonMobil Solid State Chemistry Faculty Fellow, a presidential early career awardee for scientists and engineers, and won the Excellence in Storage Technology Commercialization Award from the Colorado Clean Tech Industry Association. In 2012, she was awarded the Margaret B. Hazelus Award at Colorado State University in recognition of her mentoring efforts. And in 2014, she received the Agnes A. Morgan Research Award from Iota Sigma Pi. She is an associate editor for chemical communication and has been inducted as a fellow of the Royal Society of Chemistry. Her batteries are currently on display at the Smithsonian Institute, Lemelson Center in the Places of Invention exhibit. The title of her talk is Designing, Developing, and Manufacturing State-of-the-Art Rechargeable Batteries. Now, without further ado, I will turn the time over to Dr. Prieto. Dr. Prieto, the screen is all yours.
Thank you so much, Sushmita, for that really nice introduction. It is a huge honor to be included in this incredible list of women that you have this semester. I am a solid state chemist. And here, let me share my screen. And so the way that I came into electrochemistry actually was thinking about electrochemistry as a really powerful synthetic tool. And so that's what I want to try to show you today. I am definitely a synthetic chemist by training. I am not an engineer, but in the attempts to commercialize the battery that I will show you today, I've also gained a great appreciation for the challenges engineering poses in terms of trying to scale a technology that, you know, might work well in really small scale in the lab, but isn't practical at very large scale. So I'll try to show you a little bit of the fundamental research for how we arrived at this battery, and then also our efforts to try to scale this. So this is an older Tesla model, and the only reason I picked a car is because there is so many exciting announcements coming out every day in terms of electrifying our transportation. And, you know, companies that are getting a lot of attention for focusing on cars, for good reason, are really focused on batteries that can accelerate quickly. So that's power density, and a Tesla is particularly good at this, a 0 to 60 mile per hour acceleration in a very short time. Energy density, which is, you know, how far can you drive on a single charge. It's unfortunate though that in sports cars, if you're a very aggressive driver, the amount of miles that you can drive on a single charge decreases. So the more aggressive the driver, you know, the shorter that distance is. But the cost of the batteries currently is a major concern. And I think the price of batteries has dropped much more dramatically in recent years than people anticipated. And so that's pretty exciting in terms of thinking about electrifying transportation, not only for passenger vehicles, but if we think about long haul trucking, or more importantly, if we think about, say, scooters, ultralight delivery vehicles all around the world, we have a real opportunity to be able to use batteries more effectively than, say, internal combustion engines. So as a chemist, what I think about when I think about batteries is not only power and energy, but can we try to think about integrating ideas for low-cost sustainable manufacturing from the very beginning and build those strategies in at the cell level? And more importantly, can we make these batteries really safe? And so the problem is that there is no one perfect battery for every application, but certainly what we need to do is develop a whole portfolio of different energy storage strategies so that, you know, we can really meet all the requirements of the chart that Partha showed at the very beginning. Okay, so you all know how batteries work. I know everybody listening in this webinar is an electrochemist. The reason I'm showing this particular graphic is because I want to highlight that the way I think about batteries is really tied to diffusion rates. So certainly solid state diffusion of ions from the surface of an electrode to the center of that electrode is slow at room temperature. But also the distance between the electrodes is really important. And so, you know, we already know that if we make very high surface area electrodes, we can achieve pretty fast charge rates within that electrode, but the distance between the two electrodes is still a significant challenge. So if you could combine really high surface area electrodes, but also make the anodes and the cathodes really close to each other to reduce that diffusion length, it would be possible to build a device that would be a cross between a battery and a supercapacitor. So ideally something that has a very high energy density, but also can charge and discharge very quickly and have a very high power density. So that really is the goal of what my group and I are trying to do and what my company is trying to commercialize. And that requires really thinking about a new architecture for a battery. I think you're all probably very familiar with this figure as well. What I'm trying to highlight here is all current battery architectures are what I call two-dimensional batteries. They're layers that either get stacked or rolled. And the challenge with this kind of an architecture really is that if you want to increase the energy density of these cells, you make the layers really thick, and so then the power suffers. If you make the layers really thin, you can get high power batteries, but then the energy density suffers. And so what we would like to do is try to combine high energy density and high power density. And in my opinion, the best way to do that really is to make a 3D battery. So what I'm showing you here on the top, I'm going to try to have my little arrow show up if I can. Hold on. Let's do this. So on the left here, I'm showing a battery that has high capacity, so thick layers. The trade-off then is if I want fast charging, so over here on the right, I have to make the layers thin. But what if instead we could interdigitate all the components? So the path length between the anode and the cathode at every point in the battery will be really short, but we can make use of the Z height of the battery to store a lot of energy. In that case, we propose that this architecture could give you high capacity and fast charging, And if you use the right materials and you eliminate flammable liquid electrodes or electrolytes, in theory, this battery should be really safe. Okay. So I want to be really clear that we are not the first to think of this. There's been a lot of really beautiful work, both on the modeling side and on the synthesis side, trying to build 3D batteries. And there are a variety of different approaches to that. I chose these two simply because they were both made using solution method approaches in theory that could be made mostly on a benchtop. And so I thought they were really elegant in terms of their simplicity. These are the two examples that really inspired a lot of how I think about 3D batteries. On the top is an example from Andreas Stein at the University of Minnesota, where he uses silica spheres to create an opal structure, deposits carbon framework all around the silica spheres, and then chemically dissolves away the spheres. You fill the inside with a polymer electrolyte, a very thin layer, and then, and that's this orange layer right here, which is really thin. And then you fill in all the remaining void space, in this case with vanadium oxide as the cathode material. So the challenge that his group had at the time was that the polymer layers were very thin, so there were some pinhole defects. And so what that leads to is basically a non-charging behavior or a very leaky capacitor-like device. The example on the bottom is from Deborah Rollison's group at the Naval Research Lab. This would have been the highest power density 3D battery by far because the surface area is so high. This was a carbon aerogel structure that was then coated with a polymer electrolyte. And then they tried to fill in all the remaining space with ruthenium oxide as the cathode material. This also had challenges with pinhole defects in the polymer. So again, sort of leaky capacitor-like behavior. But the Rollison group was able to pivot the structure and make some really beautiful capacitors and actually also move into zinc air batteries and new chemistries. So the take-home messages from these approaches is that it is very difficult to integrate different types of materials. But also the electrolyte layer is absolutely critical because for really high power, that layer needs to be very thin. It has to be electrically insulating and ionically conductive, and it needs to function as the separator as well as the electrolyte. So mechanically, it has to be quite robust. So I learned a lot about the challenges for each component from these two examples. And from that, we tried a variety of things that did not work, but then we arrived at this approach. So let me tell you a little bit about the design rules that we chose at the very beginning, and hopefully that will give you an appreciation for how incredibly patient my students at the time were. I was never intending to try to start a company or commercialize this. So I was really thinking about what would the best battery be in terms of performance? How could we build in really rich projects for every piece? How could we use this as a tool to really teach my students about the importance of collaboration and of understanding each other's projects, and my personal goals for sustainability and environmentally friendly manufacturing? So the way we started was actually backwards. We made a list of all the equipment we were not allowed to use. So nothing that was really expensive or slow. So at the time, some of the tools we listed that we weren't allowed to use were things like very high vacuum deposition, nothing that required line of sight, so no sputtering methods, nothing that was slow, so no atomic layer deposition, and nothing that required really high temperature. From that, we arrived at electroplating, and electrodeposition is used very widely in many industries. It's used to coat everything from jewelry, car bumpers, to Boeing 787s. It's used in very high precision in the semiconductor industry. So it's a really good tool for making materials and coating materials. The next level of restrictions we used was that we wanted to make sure we didn't use anything toxic if possible. And so we wanted all of this to be made out of water, ideally in a way where the water could be recycled. We wanted the chemistry to be robust enough that it didn't have to be done in a clean room. It could be done open air just electroplating baths like what the semiconductor industry might use. And we wanted it to be very high throughput. And then finally, what we did is we made a list of physical parameters for each component of the battery before thinking about specific compounds. And the reason we did that is because I didn't want us to be limited by compounds that I knew of. So for the anodes, we wanted materials that could store a lot of lithium per unit volume. They had to be electrically conductive and thermally conductive because we wanted this battery to be able to dissipate heat well. And more importantly, it had to be something that could be electroplated. So from step number one, the way we start is we use copper foam as our substrate. This we buy by the roll, and then we just punch out the shape that we need for the battery that we're trying to build. Copper is a very common current collector for the anode side of a lithium-ion battery anyway, but it's a really good working electrode. The surface area to volume of that foam sets the theoretical maximum for the power density of the battery. So in theory, this battery should charge and discharge 5 times faster than a 2-dimensional battery made of the same material. We use that as a working electrode, and then we electrodeposit our anode. This purple color I'm showing you in step 2 is copper antimonide. And that's a lot of the data that I'll show you today is from this compound. Copper antimonide is an unusual choice in a way. It is similar in terms of the conversion electrochemistry to silicon. It doesn't have as large of a theoretical gravimetric capacity as silicon, but it does have much higher electrical conductivity and much higher thermal conductivity. And more importantly, it lithiates at potentials more positive than the plating of lithium metal. So that's how we prevent, or in theory, inhibit lithium dendrite growth at high power conditions. Because the anode is a good metal, we can use it as the electrode to coat the whole structure with our polymer electrolyte. These are custom-made proprietary polymers that we've developed. They are good electrolytes on their own, but they are mechanically flexible. So they expand and contract as the anode lithiates and delithiates. And in theory, this leads to a much safer battery because we don't have any free electrolyte. The high rate data I will show you today, though, to be very clear, is not a dry polymer. We do gel it with a little bit of a liquid electrolyte. Again, there's no free liquid, but there is liquid gelled in the polymer, and that's what enables very low temperature performance and also the high rates. And then at the end, we fill in our electrode with industry available cathode materials. We have modified the slurry chemistry a bit so that it is water-based. So the drying process is actually quite important to eliminate water here. And then we apply an aluminum mesh current collector, and I'll show you that in a moment. So our company is very proud of the fact that this is an entirely water-based process. It is very fast. The equipment is really low cost. And we've worked quite a bit on scaling some of the batch yields for the different steps of this process so that we can build larger and larger batteries. We have pivoted a bit in terms of our industry targets. And so our partnerships now are Stanley Black & Decker, as was mentioned in the introduction. So everything that you might use on a construction site. So high power tools, non-roadworthy vehicles. And then our newest partnership actually is with a startup company called Hercules Electric Vehicles. And they are building high-end pickup trucks, actually. Okay, so as I mentioned, we use aluminum mesh as our current collector, and this is a better image of what this looks like. The mesh actually does cover the whole surface area in this arrow here of the cathode slurry, and we dry the cathode slurry around the aluminum so that we have lower impedance on that side. And then to build capacity, we stack layers of this 3D battery. So the thickness of each layer is set by the thickness of the foam that we buy. And then we calendar that whole layer a bit to densify the structure and to densify some of the cathode slurry. And then we can stack these again to build higher capacity cells. So the electroplating is quite fast. What I'm showing you in the photograph on the bottom left is the copper foam. with a tab that's ultrasonically welded. And that contact tab is actually quite important. That also has to have pretty low impedance to have good performance. And then the image on the right is one of those foams after a 2-minute deposition of the copper antimonide, and it is conformally coated. There are no binders, there's no post-processing. It's just a very thin layer of a dense electrochemically active anode material. So I want to switch gears just a minute to talk about some of the fundamental research and why that's important for developing new battery technology. I told you at the very beginning that I wanted all of this to be made out of water. And the challenge when I first started as an assistant professor was that there were really very few examples of high energy density anode materials that could be directly electroplated from aqueous solutions. And so my very first student, Dr. James Mosby, who now actually is a senior engineer for Panasonic in Nevada with Tesla, he had just this brilliant idea of using very simple coordinating ligands to bind to the copper in the antimony in solution. So what I'm showing you on the top right is the structure of citric acid. Remember, I asked that we use as low toxicity chemicals as possible. Antimony we can't avoid because it is part of the anode, but the citric acid is actually just a really common food preservative. It's soluble at really high concentrations, and the carboxylic acid groups deprotonate at different pHs, and so they bind pretty strongly to the copper and the antimony, and this is important for the direct electrodeposition. The cyclic voltammogram I'm showing on the left, in black, is the CV scan for these two metals in solution at low pH. And the problem is that at potentials just about approaching sort of negative 400 millivolts versus SSE, you see the evolution of hydrogen. And so you never get to a potential negative enough to be able to plate antimony. If you use citric acid though, and you raise the pH, you dramatically extend the electrochemical window. Here you can see two reduction events that correspond to the deposition of copper and antimony. Copper is a really anomalously fast diffuser, and so you nucleate and grow copper antimonide. And the citric acid actually helps to absorb onto the electrode surface, so you don't evolve hydrogen until very negative potentials. The as deposited copper antimonide is crystalline at room temperature, and this is quite important because we need the electrochemical performance of copper antimonide, not the mixture of copper and antimony. So this was actually my first paper as an assistant professor. It led to the first patent, which led then to the founding of the company. We have studied this compound for quite a while, as have many other people. I think of people like Christina Edstrom in Europe, Michael Thackeray at Argonne National Lab. So this compound has been of interest for quite some time. On the left, I'm showing you a plot of the potential versus lithium, lithium plus on the y-axis, versus specific capacity on the x-axis. The first cycle is the solid line, and the dotted cycle is the second cycle. And what I want you to get from this is there's actually a pretty significant irreversible capacity loss on the first cycle. There are also multiple plateaus, which tells you that there are intermediate phases that are accessible. And if we take that data and on the right plot the differential capacity plot as a function of potential, we can identify what those intermediates for each peak are, how they change as a function of not only cycle number, but actually also rate. We can identify what the stable stoichiometries are for the intermediates, and use all of this to understand really the kinetics of how this anode behaves under different charge rates. We can also image thin films of this compound, and I'm showing you this because I know there are a lot of mechanical engineers listening. The mechanical stresses in dense anodes like this one, like silicon, and for sure, you know, the plating and stripping of lithium metal are quite challenging. So in these images, what I'm showing you is in the middle, the differential capacity plot. So the lithiation and the delithiation. And then the numbers correspond to where we stopped. disassembled the cells, and then imaged the film. And what you see when you start from just the blank film going to voltage number 2, then 3, then 4, you see the buckling of this film as it lithiates. So the volume expansion is significant. You can see there are definitely some defects on the surface where the buckling is getting pinned. And then by the time you get to 0.6, where you've completely delithiated, most of that mechanical stress has dissipated, but you see that there are some cracks that remain. So one of the advantages of electrodeposition is we make dense films that don't have any binders, and that means that we can study the fundamental properties of these materials without having to worry about the complications of the additives and the binders that are typically used. The trade-off, though, is if you make a high-loading thin film, mechanically it's not stable and it does pulverize. This is a film that was less than a micron in thickness. You see that it does pulverize over many cycles, and that leads to delamination. So this is another advantage, actually, of using a 3D battery. If we use a 3D structure, you can get very high loadings per square footprint, but locally, the layers are quite thin, and I'll show you that in a moment, and they can dissipate this mechanical stress a lot better. Okay, so in my academic group, we just do normal electrodepositions in beakers. You know, we think a lot about things like the counter electrode placement, surface area, pre-treatment of the substrates, and how to clean the surfaces. We make pretty reasonably sized foils that we can characterize with X-ray diffraction, scanning electron microscopy, and then we can punch out discs from those foils and assemble them in swage lock cells. We use these because we can disassemble them pretty easily at the end and do postmortem analysis of what the films look like. You know, and then we can, once we build these cells, we can put them on a cycler and do all the electrochemical experiments that are normal for batteries. One of the key aspects, again, that I think the fundamental research is important for is identifying degradation mechanisms. And I mentioned at the beginning that copper is an anomalously fast diffuser. So on the bottom left, we did an experiment where we were trying to understand why batteries seem to die faster if they were higher in antimony composition versus higher in copper. The copper is there as a conductive framework, but the antimony is the element that actually stores lithium. So ideally you would want a pure antimony electrode. But if you do that, the copper diffuses from the current collector so quickly, you form Kirkendall voids, which is what I'm showing you in the cross-sectional SEM at the bottom of the slide. And those voids weaken the contact between the active material and the current collector. If you deposit, say, a very thin layer of nickel metal, the nickel doesn't diffuse. You can cycle that battery for a very long time and you don't get this mechanical weakness. So the plot in the top of the slide in the middle is capacity versus cycle number for a variety of compositions. So from pure antimony, low copper to copper rich on copper substrates and nickel substrates. And you can see that we can really tune the electrical conductivity of the anode, its mechanical stability with the substrate, and get pretty good capacity retention for a particular composition on a particular interface. And so this is really important then for being able to incorporate these materials into a 3D battery because the interfacial surface area is very high. So any degradation that happens at the interface is exaggerated in this kind of a architecture. Okay, so this last part is pretty quick, just some images. I'll tell you the company I started in 2009. Remember, I was not intending to start a company, but it was a good way to be able to accelerate the purchase of good equipment for my students and to try to really focus on making this a practical solution for a market need. Over the years, we've grown quite a bit and tried to establish some strategic relationships because I thought it was really important that we have a good dialogue with potential customers. The big challenge was trying to go from very fundamental research to a battery that was really practical. And so in the last couple of years, we've finally been able to develop good prototypes. We did package our 3D anode with traditional liquid electrolyte, normal separator, and normal cathode laminates to have some third-party safety testing completed. And that was really important for demonstrating the stability of the chemistry of the anode. Now we're focused on doing the same thing with our fully integrated 3D solid-state cell. It does function over a broad temperature range, and we focus quite a bit on the patents. So the IP protection is the major use of proceeds for the company right now. We do protect our technology around the world, but mostly in countries that really focus on battery technology and have good markets for batteries for a variety of different applications. Right now, again, the focus is really high power. And so we have actually ended our partnership with Intel. They have divested from everything. They initially championed us because of our potential to be included in wearable devices. And Intel has decided they are not going to go into the wearables market anymore. So we have pivoted and stayed with Stanley Black & Decker, but added Hercules for high power, and really working on trying to ramp our manufacturing. So we are this week actually closing our Series C and moving toward building a larger manufacturing facility. So this is what the battery looks like. This is the copper antimonide deposited on the foam. You can see that it deposits faster at areas of high curvature, but it does conformally coat this 3D structure. Once we add all the components, and I'll show you a picture of that in a moment, you do have a freestanding dense 3D battery. This image is showing you the aluminum mesh on the bottom and the cathode slurry dried around that. So when we test our batteries, we always test the 3D battery versus a 2D battery made of the exact same materials, made in the exact same way. So what I mean by that is we take a copper foil, electrodeposit our anode, electrochemically polymerize our polymer electrolyte, and then spray coat our cathode. And in order to really compare those, it's important that they have the same capacities. And so what I'm showing you on the top left is the footprint of the 3D battery. And on the top, it's that teardrop shaped battery versus the 2D battery. Those both have the exact same capacity. But what that's showing you is the 3D battery is doing a much better job of using the Z height. So pack a lot more material in a smaller footprint. The SEM image on the bottom left is a cross-sectional image of part of the foam. You can see the copper tendril in the middle, the really thin copper antimonide anode, the electrodeposited polymer electrolyte, which is charging a little bit under the electron beam, and then the cathode slurry. So the 3D structure can handle about 5 times higher current per footprint than the 2D battery can, with much better capacity retention. And I'm going to show you a plot of that. Under controlled depth of discharge, we can achieve about 300 cycles. So a big effort right now is improving our cycle life. When the polymer is gelled, this battery does really well at -30 degrees Celsius, and it's stable up to about 120 degrees. And if you click on that YouTube link, you'll see a video of us fully charging a battery, cutting it open, and there's no thermal runaway, no fires. The battery actually does keep working. So we've been able to sort of combine some of the best of a true solid state battery, but by gelling the polymer, we are able to achieve low temperature performance, but still maintain some safety. So this is what it actually looks like in real life. This is the 3D battery. You can see where we weld to our current collector, and that's this weld spot right. Oh, one second. This weld spot right here. This is going to stay as the tab for the anode side. And in the image on the right, you can see that copper antimonide coated with the polymer electrolyte. The polymer is, for the most part, clear and colorless. And we've worked pretty hard to make sure that we have no pinhole defects. And we've developed some IP for how to ensure that and how to coat all the way through the material. And then spray coated with the cathode. Again, this image doesn't have the aluminum mesh, but you can see some of the texturing from how the cathode slurry dries. And again, a better photograph on the bottom right of the same capacity for a 3D battery versus our 2D battery. So this battery does handle high current discharge. In this experiment, this is a small cell, it's a 20 milliamp hour cell, but our anode, our polymer electrolyte, and an MC811 as a high voltage cathode. We pulse discharged 180 milliamps for 3 seconds, followed by a rest. And this battery can handle that repeatedly. So we did 10 pulses and then a rest and then another 10 pulses. So this was really important for Stanley Black & Decker to be able to demonstrate that this battery could handle high discharge currents without shorting, without having sort of a leaky current, but more importantly, to be able to do this at room temperature. And then just to wrap up, this is the hallmark of a 3D battery, which is if you compare discharge capacity retention at different discharge rates. The green data are 2 3D batteries, and the red data are 2 two-dimensional batteries. So again, all the materials are the same. They're all made the same. The only difference is the architecture. And what you can see is by the time you get to 5C, 10C, 20C discharge rates, the 3D battery is retaining capacity significantly better than the 2D battery. But when you slow back down to C divided by 10, the capacity retentions recover. And so that's telling you that the chemistry of the materials is pretty robust. And the 2D battery does recover, but at high discharge rates, the sort of conventional 2D architecture just can't keep up with the 3D architecture. So now to switch a little bit back to sort of fundamental research, my group is actually quite interested in expanding the kind of chemistry that we look at. And all the elements here that I have circled in red do combine with antimony to form a variety of intermetallic compounds that can react not only with lithium actually, but also with sodium to form a variety of different end members. So the general formula of a metal antimonide with lithium or sodium, you make the lithium antimonide plus the metal compound. And these the 3 compounds on the bottom are ones we're studying pretty heavily right now because they have very different conversion chemistry, very different lithium and sodium reactivity. And so we are quite interested now in thinking about new applications and batteries that can be made potentially for applications like grid storage, wind farms, grid stabilization. So larger batteries, potentially more robust, ideally earth abundant elements. And so I think the battery chemistry on this slide, in particular the solid state chemistry, is quite exciting. So with that, I want to thank my group. So all the fundamental research that comes out of my group, if I think it has potential commercial impact, gets licensed to my company. And in some cases, when my students graduate, they can work for my company if the timing for that is right. And a lot of the basic electrochemistry, the more ambitious, I would say higher risk experiments are funded by the Keck Foundation or the Research Corporation for Science Advancement. So with that, let me stop sharing, and I hope I did okay on the time. And Partha, I don't know if you want to take questions now or if we should wait at the end for everybody.
We're going to take questions at the end, and we'll kind of merge it with the panel. Thank you so much, Emmy. Really appreciate it. Thank you. So, Sushmita?
I think I'll introduce our next speaker. Thank you for the wonderful talk, Dr. Prieto. So our next speaker is Dr. Lakshmi Krishnan from GE Research. Dr. Krishnan is a senior scientist in the material organization at GE Global Research, Niskayuna, New York. She's a trained electrochemist and technical project leader with over 20 years of academic and industrial research experience. Lakshmi earned a PhD in electrochemistry from Princeton University, developing synthesis routes for polymer composite membranes that showed lower hydrogen permeation and improved performance in polymer electrolyte membrane fuel cells at high temperature, low humidity operation as part of a DOE subcontract. At Rensselaer Polytechnic Institute, Lakshmi was the electrochemical lead for a $2.5 million DOE project working with BASF to implement ultrasonic sealing for fuel cell stack manufacturing. At GE Research, Lakshmi served as the integration lead for a 5-year $15 million DOE-funded EFRC to develop fundamental basis for an entirely new high-density energy storage system that resulted in the discovery, design, and understanding of new materials to advance DOE's mission in energy and environment. As part of this project, Lakshmi collaborated with students and faculty at Yale, Stanford, UC Berkeley, and Lawrence Berkeley National Labs to develop novel fuel cell systems. In 2016, Lakshmi became the project lead for development of high-temperature materials by electroforming, an additive manufacturing method of fluid delivery systems that provided up to 40% cost reduction for aircraft engines. Lakshmi successfully completed the esteemed GE Crotonville project management and is well trained on project definition, stakeholder management, planning for execution, project measurement, communication, and handoffs, which she leveraged to transfer technology from concept to commercialization of the electroforming technology. She has also worked and led various technical projects in partnering and coordinating technical projects with Critical Materials Institute CMI, ARPA-E, ONR, and national labs, and holds several patents in this space. The title of her talk is Journey in Electrochemical Systems, Methods, Materials, and Manufacturing at GE. Now, without further ado, I will turn the time over to Dr. Lakshmi Krishnan.
Thank you, Devanjali, for that very nice introduction. And thank you, Partha, again, for the opportunity. I also want to thank the ECS chapter at Purdue for giving me the opportunity to share some of the electrochemical experience. I think it's hard to beat Amy's talk, but I'm going to do my best to give everybody a flavor of what we do at GE. Some of the energy storage projects that we worked on and other electrochemistry related projects as well. So I will start sharing. Before I do that, let me just quickly, can you guys see my YouTube screen?
Yes, we can see your screen.
You can see your screen. Yeah.
Very short 30-second video about GE research. And then we can go on and dive into the specifics of who we are, what we do.
I think we can see just the PowerPoint, but not the video.
Yeah.
I think I have to do.
Yes, now we can see your YouTube.
So a lot of people know about GE, I'm sure, but I do want to.
Hi, everybody. Welcome to tonight's webinar info session on GE Research and the Edison Engineering Development Program. My name is
So a lot of you have heard about GE, but GE Research is its own dedicated facility that we're located in.
Dr. Krishnan, we can't see your PowerPoint presentation. Still in the Zoom link.
You see it now?
Yeah, if you can click on the display setting and switch the presenter mode, it's in the.
Better?
Not yet. Display setting and then switch to, I think, a swap screen or duplicate, something like that. Yeah, you could click on display settings.
I did.
And then there is a, yeah, now
Yeah.
duplicate.
Oh, duplicate. Okay.
Yeah. There you go.
All right, great.
Perfect. Thanks.
Okay. Okay. Now it says my window is closed.
Yeah, sorry. They have to reshare it again, I guess.
Is it? Can you see it now or no?
No, not yet. No screen now.
I'm telling you, I can do complicated science. I can't figure this out. Let's try it one more time.
Yeah.
All right. Duplicate. Is that good?
Good to go. Thank you.
Great. Okay, so let's try it again. So GE Research, we are a separate arm of General Electric Company, and we are located in Niskayuna, New York. We, upstate New York. We're about 150 miles north of New York City. And this is actually, the Niskayuna location is actually our corporate research headquarters. And we also have a GE research facility in Bangalore, India. And we work with them closely on many of their projects. So we were founded by Thomas Edison almost 120 years ago. Our R&D facility spans more than 300,000 square foot of lab facilities and collaborative spaces. And our labs are actually very domain specific. So as Debanjali pointed out in the introduction, I belong to the materials organization. We have electric power systems, we have additive manufacturing, we have electronic systems. So there are several domains within the research center. And we're enabling deep scientific R&D of custom solutions. Throughout this presentation, we'll look at how GE Research fits into GE's advanced technology framework, but also the future of our industries. Throughout our history, we do like to brag. So GE Research scientists and engineers have distinguished themselves. We have tens and thousands of patents. We even have 2 Nobel Prize winners in chemistry and physics, and the list of inventions that we've created that are basically form the new frontiers for our industry. We do have several firsts here. If you look in the left of the most part of the slide, probably the most important invention was the electric lamp. There's a saying here that goes in GE that says we never stop inventing the light bulb. Our research engine is fueled by technology and capability. And like I said earlier, we have deep expertise in many of these domains, includes materials, artificial intelligence, additive manufacturing, biology, and applied physics. Our portfolio, if you focus on the middle there on differentiated technology, is basically building background IP. And this is what makes us really unique. For all of our projects, we assemble interdisciplinary teams across all the domains that I had mentioned earlier. And that really gives us the ability to think outside of the box, puts a fresh perspective on problems, and find unconventional solutions. And I do want to point out that a majority of the research we do, we just don't pack it up and put it on a shelf, or we don't stop after we publish our IP. We do have the ability to have them field tested and deployed in real world applications. And on the right here, there are some of the businesses that GE Research has had a hand in. As you can see, we've had GE Research is contributing to GE Power, the healthcare business, the aviation business, and our renewables. And we are able to touch all of these products either for fundamental R&D with material development, or additive manufacturing to make them lighter or cheaper. We can also do digital controls. And we also work with our healthcare business to optimize a variety of healthcare systems that include portable ultrasounds and neonatal care, especially for regions in the world where it is hard to access healthcare. I'm going to try this one more time. There is another video, but I do want to give context of why I do want to play the video. So another significant contribution from GE Research to gas turbines and aviation is the research and development of ceramic matrix composites. These are called CMCs, and this work was actually kickstarted at GRC about 40 years ago. And since then, we've made steady improvements to raise the temperature tolerance of these metals by 300 Fahrenheit. And more recently, GE was recognized for technical achievement for commercializing the CMCs in the aircraft engine. So when I show that video, you'll see that the newer aircraft engine has a lot of CMCs that were actually field tested, but now they're actually flying. It's impossible to think about ceramics flying. Right, so it's such leaps and bounds in R&D and development that happen here. There's also some additive manufacturing that's shown in that video. and the Predict software, which is also used for digital controls. That was also developed at GE Research, and we had a major contribution across all of those. So I'm going to try this again. Apologize. Okay. All right. So that was, to kind of give a flavor of how we work, what kind of businesses we touch on. But recently, in addition to supporting our businesses, we also have a longstanding history of partnering with government agencies. We share common technology interests and goals. In energy, especially, we're pushing advances in clean energy like the entire world is trying to do. And we're trying to do that to differentiate GE's products and contribute to the goal of a more sustainable planet. So we're currently working on several projects in the renewable space, energy storage, and also the decarbonization space. So GE Research recently announced actually a Center for Decarbonization that's going to be solely looking at those efforts. All right. This is all of the technical domains. I mentioned at the beginning, I belong to the materials organization here at GRC, but this is all the list of all the domains here. We're very interconnected and collaborative across the center. And if you focus on the right, you can see that we lead and contribute directly to some of the products that are here. Some of which you actually saw in our aviation video. And this, this kind of work, it includes new product focus. We improve on existing products. And sometimes when there is a problem in the field, the businesses would reach out to the team at GRC, and then we would end up doing a root cause analysis to understand and fix that issue. The other area of focus here is this horizontal, which is right in the middle. This is where you have one specific technology area that will touch upon several of the businesses. So if you look at additive here, the additive horizontal is responsible for developing advances across missions in machines, materials, digital, and also identifying new additive modalities. And then the exponential part here, that portfolio is basically creating the future in each of those technology spaces. I won't walk through all of them, but if you think about the bioelectronic medicine, that's almost like using ultrasound replacing drugs to treat autoimmune and metabolic chronic diseases. And we will use AI to deliver therapy to specific targets of the body, almost like a digital drug factory in no pills, if you can imagine that. So with that introduction, I would like to dive into a bit more specific on some energy storage and conversion capabilities and some of the projects that we have. We have an energy storage group where we have the ability to characterize the initial performance of any electrochemical cell. We have, fully automated single cell battery cycling equipment, but then we also do characterization with electrochemical impedance spectroscopy and high precision colorimetric analysis. We also do autopsies, like Professor Prieto mentioned in her presentation earlier, which is very valuable in trying to understand our materials and make improvements. We also develop degradation models for batteries and host them as cloud-based microservices for integration into advanced analytics for sales and field monitoring. In addition, we also develop advanced materials and engineered components for next generation energy storage. So those are some of the ongoing projects here. There are some of the past equipment, projects I have listed too. We have coating equipment, so we do thermal spray routinely, and processing equipment in support of our advanced energy storage materials development. One thing I would like to highlight at this time is our characterization team. We have a dedicated group of scientists and analytical chemists and engineers. This is a separate organization. I could even call them a domain. They do belong to the materials domain. But this team is actually dedicated to do characterization like high resolution SEM, a variety of X-ray techniques, elemental analysis, CT imaging of batteries after the autopsy is done, or even before the autopsy, to basically understand our material systems better, point of failure modes, and so on and so forth. We also have a very strong background in high temperature electrochemistry. We did have a fuel cell business, a solid oxide fuel cell business that was recently acquired by Cummins, but we have decades of experience in high temperature energy storage, ceramic electrolytes, and molten salt chemistry. The team here, the energy storage team here, has experience with solid oxide fuel cells from 1 watt to 1 kilowatt of power in a number of single cell and stack size scales. And we actually produce the world-class metal supported solid oxide fuel cells. So GE developed the thermal spray technique to be able to develop these metal supported solid oxide fuel cells. In the last 2 decades, we have collaborated in partnership with universities, US national labs, external companies, and also GE customers in this space. And right now we're working to combine the thermal, the manufacturing technology with redox stable ceramic and/or materials to basically produce large scale solid oxide fuel cells. So this is an ongoing DOE project, and we're partnering with the University of West Virginia for that. Switching gears here a little bit, I want to talk about some of the energy storage projects I was involved in. So right when I started working at GE, there was an EFRC, they were called Energy Frontier Research Centers. They were funded by the Office of Basic Energy Sciences to promote collaborative research to accelerate high risk, high reward fundamental research for transformative energy technologies. So the vision here was to be able to use organic hydrides in fuel cells as virtual hydrogen carriers. And so if you think about a regular fuel cell where you have a hydrogen, oxidizing into protons and electrons, here we will have a hydrogen carrier, typically an organic molecule like that, excuse me, where they will be upon electrooxidation, they will be providing the protons, and the main innovation here was to be able to use a catalyst system that will also end up reducing the same fuel. So if you can think of fuel cell as a rechargeable battery with the liquid fuel, that was the basis of this entire program. So if you compare it to a hydrogen on-demand design that includes thermal decomposition of organic hydrides, this approach was much simpler, and it does not require additional dehydrogenation catalyst or any heat exchangers. And this approach utilized the advantages of flow battery, right? So where you have separation of power and energy and ease of transport and storage of liquid fuels with fuels that have the energy systems similar to the current hydrogen PEM fuel systems. Two major challenges that I worked on in this space were electrocatalysis and transport phenomena. The electrocatalysis was to address the fundamental process which occur at a single molecular catalyst level, right? So this was basically the bed where all of the electrochemistry was going to happen that would involve electron and proton transfer between the hydrogen rich, but also the hydrogen depleted organic fuel. To form stable non-radical dehydrogenation products, it was necessary to ensure fast transport of at least 2 electrons and 2 protons, right? So, and the same was true for the reverse hydrogenation reaction. The transport phenomena was to address the transport of electrons to and from the electrocatalyst and the current collector, but also address the proton transport across the polymer electrolyte membrane. So typical Nafion-based membranes or PBI phosphoric acid-based membranes were not suitable with the organic liquids. So we actually had to go and invent our own or modify our existing Nafion and PBI-based membranes to be able to be compatible with this operation. But this program, you know, there were various types of electrocatalysts, there were classes of fuels that were investigated, and there were a lot of membranes that that were also investigated, which was truly a novel concept at the time. This program started in 2010 and ended in 2015, but there was a lot of learnings that happened in terms of fuel transport, electrocatalysis, membrane selection during the course of the program. So it was really a great program to be a part of. Next one is I will touch on the Durathon battery technology this was a separate business. It was a GE energy storage business, but you can see GE Research was very heavily involved in a lot of material development. Again, you know, we did lab pilot scale advanced processes. We did fundamental electrochemistry and material models, and we did cycle life testing. You know, it was either application specific or it was for overcharge, over abuse, higher temperature, higher voltage charging, and all of those abuse conditions. We had a separate test facility at GE Research, and we were helping out our energy storage business for that. The Durathon business was mainly introduced for critical backup power. The battery can be used in uninterruptible power sources for large data centers, hospitals, where you need a continuous supply of power. The battery technology itself was patented, sodium halide chemistry, but it has existed for more than 30 years. And there was a company over in UK, Beta R&D, was the one that had this chemistry and also had a manufacturing facility. GE acquired the company, and then we kind of moved our operation to Schenectady here. And you can see the cathode structure is a sodium metal halide. It has a conductive nickel network, a molten salt electrolyte. There is a metal current collector. There is a carbon felt that's used as an electrolyte reservoir. And then there is a mix of sodium metal halide salts, which is basically the chemistry for this battery. And you can see what happens during the charge and discharge reactions. GE was using the technology to develop advanced transportation energy systems. And because of the proprietary chemistry, the Durathon will have the ability to provide backup surface for up to 2 decades. Long cycle life and deliver performances under a harsh environment, but also be completely safe. GE Research, when the business was kickstarting, the GE researchers, we continue to enhance the battery chemistry and related systems technology. And again, we learned a lot from the process. There was a manufacturing plant that was operational until about 3-4 years ago. And then the technology was then again transferred to a Chinese-based company a few years ago. Switching gears from energy storage, Partha at the beginning mentioned how important electrochemistry is. So this is a project that I worked on also as part of the Critical Materials Institute. Now, this was an energy innovation hub that was established in 2013, and it was actually led by Ames Laboratory out of Iowa. And it was basically a multidisciplinary effort to develop solutions across the materials life cycle, but also reduce the impact of supply chain disruptions, especially for rare earth metals. Right, so CMI was addressing challenges in critical materials that included mineral processing, manufacture, substitution, and end of life recycling. Again, this was also a very collaborative project with a lot of industries and national labs. And as part of this project, I led the electrochemical synthesis part of samarium cobalt nanoparticles. We were focused on developing high performance permanent magnet materials to basically accelerate the realization of exchange spring composite magnets. Now, these magnets are basically the building blocks of anything, you can think about hybrid electric platforms. These permanent magnets are very important. So we were able to successfully develop an electrochemical synthesis method to produce nanograins of the samarium cobalt with exceptionally high purity, almost 99% phase purity. And we were also able to tune and control the magnetic properties, the quality. We improved the quality of our nanoparticles, and we were also able to scale up our process to 2 grams worth by electrochemical synthesis. So we were able to overcome some of the issues that the mechanical synthesis aspect of this was happening. So that was also a good project to be part of, and we have a published patent on in this specific topic as well. My favorite topic here, electroplating. So we have a lot of efforts, projects that are happening in the electro deposition space at GE Research. A lot of you are familiar with plating. It's a wet chemical means of depositing coatings onto substrates. Like Professor Prieto explained in her talk earlier, it is fairly cheap, and if it's an aqueous-based process. And all of these coatings can be done for oxidation protection, corrosion protection, or frictional resistance. That's just a few examples of applications of electroplating. There are several types of electroplating. The conventional electroplating, you can plate them up to thousands of microns. It is typically done on conductive surfaces, and it plates along an electric field. So it's a line of sight process. There is electroless plating, which can be done on non-conductive surfaces to make them conductive. We do this routinely where we're given pieces of plastic that are additively manufactured to make them with a smoother texture, basically a cosmetic improvement, right? So we would initially make them conductive by doing electroless plating on this. And all of these processes are, have been commercially available, industrialized for several years. So one of the best examples of electroless plating is doing electroless nickel in printed circuit boards to avoid oxidation. In addition, we also do electrophoretic deposition. This is where it's for non-metals, so ceramic slurries, for instance. We basically reduce the number of steps when we do electrophoretic deposition as opposed to a conventional, dip and spin method on substrates. So here at GE Research, we develop materials and processes all the way from research stage to commercialization. We do new material development tailored for specific applications. When we had our battery business, we actually developed a nickel plating process for sealing rings. We do chemistry. We actually do chemistry and process development on site. Right? So I have worked on nickel and nickel-based systems. We do precious metal plating for turbine airfoils, and we have the expertise and capabilities for doing chemistries anywhere between 1 liters to 1,000 liters. In addition to new material development, we also do cost and effect analysis. So one of our international businesses had an issue with their copper plating system where they reached out, heard about us, reached out, and I traveled to Italy to understand the issues and help that team out with implementing process improvement changes. So they were able to improve and make their plating system more robust. And I do want to just, this picture doesn't mean much, but typical, this is a 250 liter plating tank that sits in my lab. And I wanted to show this example of how we develop process. So there's bath temperature on the x-axis, there's current density on the y-axis, and you can see how our coating morphology is completely different by tweaking all of these parameters. So we routinely do both chemistry and process development here on site. One other project, this is my last slide, I'm leading on, is on material development for electroforming. Now, electroforming is also a kind of electrodeposition. It's very similar to electroplating, but what you do here is you have the metal or alloy that you're plating, you put it on a mandrel. We don't call it a substrate, we call it a mandrel, because after the process is complete, when the metal or the alloy is coated, the mandrel is removed. So now you have a freestanding article with the shape of whatever, the freestanding article is whatever shape of the mandrel that you put in the bath. Now the chemistry and processes are very similar, like electroplating. And I would also like to think of electroforming as one of the additive manufacturing technologies. You have binder jet, cold spray, and DMLM, where you are building your material layer by layer. And electroforming is basically the same thing. You're building your metal or alloy of interest layer by layer. Why is this important to GE? Our aviation business has 3D printed fuel nozzles, not by electroforming, not yet, but one of these other modalities, and they have seen up to 25% fuel savings and 35% in production costs. So it's a very attractive for our businesses. Why is electroforming better than the other additive manufacturing? Because it's very well suited for large, thin-walled parts with complex geometries and with very tight tolerances. So if you look at one of the manifolds here, you can see how you have it's a very complex shape. It's not very straightforward. There are twists, there are turns. So electroforming is very suitable to be able to manufacture components like that. Typically, the way they do it today, these complex geometries are made by what I call subtractive manufacturing. So they typically take a sheet metal and they do 24 to 25 different processes to it, including brazing, casting, welding, etc., to be able to make that shape. But by moving over to electroforming, we can basically reduce those steps to 4. So you print the mandrel, you remove the mandrel, you electroplate it, and then you remove the mandrel. And I say 4 because sometimes you might need to do a little post-processing, but most of the times the electroforming part is good as it is. You can use it straight out of the box. So we think by moving over to electroforming, we're able to reduce weight and cost and energy associated with labor in manufacturing. And other additive modalities that I've shown here, they typically use metal powders that are procured and melted. There are special platforms and they are custom built for one set of products. But with electroforming, it's a very low cost, it's an aqueous-based process. And I can, as I show here, it is extremely scalable, right? So you can see that you can electroform flexible printed circuits in the micron scale, all the way to helicopter heat shields. These are commercially being made by a company called Electroforming that are, in the meter scale. We do have a couple of limitations. The deposition rate is low. So if you're used to higher build rates with additive manufacturing, our dep rate with electroforming is typically 1 to 3 mils an hour, but that's independent of the part surface area, right? So it would take you the same amount of time to electroform a paper clip or a helicopter heat shield. Another limitation that's shown here is that the limited material selection. By that I mean, when you call a plating company or an electroforming company, you typically will be offered one of these three chemistries. So you can see that there is not really much high strength, high temperature alloys that are available or that can be manufactured by electroforming. So at GE, I have led projects since 2016. We are working on developing nickel-based super alloys for temperature capabilities greater than 500 F and up to 1200 F. And we are developing these materials for 1 millimeter thick products, right? So, and that's important because typically in an electrodeposition process, your residual stresses will start to increase with your thickness, and especially on a complex part with all those twists and turns. When you take it out of the plating bath, it will be, it will be good looking, but then you leave it on the bench and come back the next day, the whole thing would have just fallen apart with stresses from hydrogen embrittlement. So as I showed you in the previous slide, there is a lot of optimization in terms of chemistry and process that are happening and are ongoing to be able to develop these materials. I'm unable to provide any more details on the materials or the products due to proprietary reasons, but this is a high risk, high reward area of interest that GE Research is involved in. And when we're successful, we would impact a variety of businesses in not just aviation. So with that, I hope I'm okay on time. I'd like to conclude my presentation. I hope I was able to provide everyone some valuable information about GE Research and some of the electrochemical areas we're working on. And I guess I will wait until the end to take any questions. And we are hiring, by the way. I don't mean to make this a marketing pitch, so please do check out that link for interesting opportunities. And thank you again.
Thank you, Lakshmi, very much. So we are going to save all the questions for the end. So please type your questions. Keep typing that as the questions come to your mind. And we're going to take some of those questions from the end. Thank you. Just go ahead, Susmita Devanjan.
Thank you so much for Dr. Lakshmi for the wonderful talk about the processes and the things going on in the GE, in the Global Research Lab. So now I will introduce our today's third speaker. Let me share my screen. So our third speaker for today is Dr. Judy Jeevarajan. Dr. Jeevarajan is the Research Director of Electrochemical Safety for Underwriters Laboratories. With over 24 years of experience in the area of batteries and a primary focus on lithium-ion chemistry, Dr. Jeevarajan specializes in battery safety research, including safety trends in aged lithium-ion cells and modules, thermal runaway propagation in lithium battery systems, characterizing the fire and fire suppressants for lithium-ion batteries, and consumer battery safety. Dr. Jeevarajan serves in the technical working group for standard organizations such as Underwriters Laboratories, Society of Automotive Engineers, International Civil Aviation Organization, Society of Aerospace Engineers, International Electrochemical Commission, American National Standard Institute, and is currently leading an effort under American Institute of Aeronautics and Astronautics to develop a space safety standard for battery system. Dr. Jeevarajan has been a member of the Energy Advisory Council at Case Western Reserve University since 2019. Dr. Jeevarajan completed UL's Global Leadership Program in 2016 and the Executive Leadership Program in 2019. She was inducted into the William Henry Merrill Society as a Distinguished Members of Technical Staff in 2016. Representing UL, Dr. Jeevarajan co-chairs a Battery Safety Council with National Transportation Safety Board As a member of the non-advocate review panel, as well as an advisory member to the Federal Aviation Administration, Dr. Jeevarajan supported the Boeing 787 investigation and the anti-SB informational forum on lithium-ion batteries. From 1998, Dr. Jeevarajan worked for Lockheed Martin Space Operations at NASA Johnson Space Center in Houston, Texas until 2003. In 2003, she started her work as a NASA civil servant, where she was a group lead for battery safety and advanced technology. Dr. Jeevarajan represented the battery group on all NASA safety panels and was responsible for approving all batteries flown for human-rated space missions. She also led the advanced battery technology work with a special focus on the safety improvements. Dr. Jeevarajan is a published contributor on battery safety. She has made more than 140 presentations at conferences and has won numerous NASA awards with the NASA Exceptional Service Medal and the NASA NASC Engineering Excellence Award being of noteworthy mention. In August 2019, she won the AIAA Aerospace Power System Award and the recognition in April 2020 by IESA as one of the leading women in energy storage and electric vehicle industry. Dr. Jeevarajan has 3 book chapters to her credit, and she earned her PhD in chemistry from University of Alabama in Tuscaloosa and holds a Master of Science in Chemistry from University of Notre Dame. So now, without further ado, I'll turn the time over to Dr. Jeevarajan. Can start to share your screen. Yeah.
Well, Susmita, I was hoping you wouldn't go through the whole thing.
You have so many achievements. I have to go through this.
Oh, thank you. Yes, I'll talk later. I think Partha wanted me to give some advice to students. I'll surely talk about it. So I was really thrilled to hear that you had a whole semester with so many women from science that spoke to the students. I'm really proud that both to Dr. Mukherjee as well as your team, Susmita and Devanjali, that you were all able to do that. Bring together some of the leading women in science to speak to the students. It's a great achievement, and I hope everyone learned a lot from that too. So the battery safety group, actually we are the electrochemical safety group, but we focus on battery safety at this time. Our mission is to advance safer energy storage through science. And we do it in several different ways. We do our research. Of course, I work with Dr. Mukherjee, as well as our own projects here in the Houston area. And we do outreach by conducting battery safety summits and battery safety council forums. And we also do trainings, webinars, present at conferences, and also publish through journal articles. So for today's talk, I just wanted to give a very brief background on why we do this work and talk about 2 topics which I have not presented to your student chapter. And that is on mitigation of thermal runaway in lithium-ion cells and modules, and also on some counterfeit battery studies that we carried out. So as you all know, thermal runaway in lithium-ion cells and batteries has been an area of significant concern in the past few decades. And we have heard about recalls of commercial lithium-ion cells and batteries. And some of them, some of these recalls are even 2 years after their entry into the commercial market. And another area of great concern has been in the transportation of these cells and batteries by various modes such as ground, air, and sea. And I think mostly what we might have heard in the news is mostly the events that occur in the air transportation. Catastrophic events during transportation has led to restrictions that were placed by the ICAO. And they said that the state of charge of lithium-ion cells and batteries should be 30% or less during transport. And there have been other field events, as my background, as Susmita read my background, she talked about the 787 incident that I was involved in. We've also seen in the past 2 or 3 years, grid energy storage system battery fires. We've heard about automotive battery fires and so on. And all of these, have led to some new regulations where, although some of them are still not in place, what these regulations are requiring is that a single cell thermal runaway should not propagate to other cells in the battery pack, or that a fire, if it is generated, should be contained within the battery itself. But given the numerous cell and battery models, as well as the combinations of electrodes, separator, and electrolytes that we're working on, and as you heard from Dr. Prieto, that there's still improvements that are being made with respect to materials in the battery world. It is not easy to just have one modular battery and say everything will be safe if everyone uses this. We need to figure out for different battery chemistries, different models, and so on, what the effect of thermal runaway propagation is, and if it is a catastrophic event, how to prevent it from propagating, or how to prevent it from even being generated. So we have been looking at materials we've been doing studies recently on thermal runaway and its propagation, a variety of configurations actually. And we also studied it at various states of charge. And we did publish a paper last year on that. But the goal of this particular work that I'm going to talk about is to study the efficacy of various materials that would prevent thermal runaway propagation or contain it within the shipping container. Just to give you an idea, in the early 1990s, when I started working with certification of batteries for space applications, we were looking at these camera and camcorder batteries and laptop batteries, which were 20 to 30 watt hour capability. Then now today we are looking at automotive batteries that might be 25 to 30 kilowatt hours, or the stationary grid energy storage that is in the megawatt hour and gigawatt hour range. So our challenges are becoming bigger because not only with usage, but also in the transportation of these really large systems, we need to develop the safety and make sure that they don't result in catastrophic failures. So the research on the mitigation of propagation, early on, this was like 2013-2014 time frame. This was again work done with Dr. Mukherjee and his student when he was at A&M. Carlos was my student intern when I was at NASA, and we worked on materials to see if we could prevent propagation. These are very preliminary studies. We looked at a radiant barrier that was a material that was 7 layers thick, and it had metal mesh, but it also had ceramic type material that was on the outside. And like I said, there were 7 layers of it. And what we found is that if we placed them between cells, it actually prevented propagation of thermal runaway. And we also looked at intumescent materials, and the radiant barrier was actually a sample that was sent to us from one of the contractors, NASA contractors, and so we had to, after testing it, we had to return it to them. And it's not used in general for battery design. It's actually used for space applications. And then we also looked at the intumescent material, where we studied this particular one, where we were able to prevent propagation, but the material itself was twice the mass of the cells that we had in that bundle. So our results are published in 2 papers in the Journal of Electrochemical Society, and I have the reference here for you to look at later. So continuing on that work that was just preliminary, like I said, we were looking at different materials in the past year and a half. And our test article is 18650 lithium-ion cells, and we're looking at a 25p configuration, because that is really worst case. When you have cells in parallel, you're going to be conducting between the tabs, and also if there is an imbalance in current, they're all at 100% charged, but they're not being charged or discharged during the test. So all that we're looking at is all the conditions are worst case, I should say, and we were looking at triggering a cell which is in the center of the configuration with the heating tape. And we looked at 4 different manufacturers with different materials, and we also looked at a container manufacturer. in order to not disclose the manufacturer's names, I have them as A, B, C, D, and E. And our target heating rate for the trigger cell was about 10 degrees C per minute. And what we did was, again, looked at a worst case configuration by choosing a generic packaging box. This is not a UN rated box, but when you buy cells online, this is a box that we usually get cells in. So we wanted to have a worst case situation all around. The next picture just shows you our thermocouple locations. We had anywhere from 17 to about 26 thermocouples that were used in the test. This is a picture of the data for the first manufacturer. I just want to make sure that I explain that manufacturer A was the material was from this manufacturer, but we were using it to create an adiabatic environment for a different test. But we thought, this is something that is not providing heat transfer. So let's look at it for mitigation of thermal runaway. So we put a Serra blanket around it, and we had this paper, K-oval paper between the cells. And what we found is that, as you can see from the plot as well as the photos, we had complete thermal runaway propagation. And I have a quick video here to show you the propagation. So it's just to show you that you get a pretty big fire. And others continues to burn. So I'll go on to the next one. This is manufacturer B. Here again, we had the refractory configuration. And this is a design. It is a type of intumescent material, but it's very light. And what we did was we gave them the drawing from our previous work, and so asked them to build a mold that we could put the cells in. And they also provided us with what they call an ejector control pouch, which we placed on top of the cell configuration or the module. And what we observed here in this case is that there was only one cell that had a slight drop in voltage, but all the other cells were at the full state of charge, and even the one that had the slight drop in voltage really did not have a thermal runaway. It was probably a self-discharge due to warmer temperatures. A quick video here also. What you will see here is that there's an initial burst of flame that actually dies down, and then what happens is the container, as I said, is not UN rated, so the container starts burning, and even the container after a little while stops burning. And we found that there was no thermal runaway propagation in this case, as I showed in the previous chart. So you'll see that, it just dies down. And I've just reduced the video for the sake of time to show you just the parts that are interesting. So as you can see, the cells are, even though there's a fire in the box, the cells do not contribute further to that, and they're not affected by it either. So going on to the next one here, same manufacturer B. What we did here is, without the pouch, we carried out the test, but with the same block mold, and we found that there was no propagation at all. And as you can see, all the cells held voltage. The next one was 33% state of charge. We found that at 100%, we do not have any propagation. So we wanted to see how 33% behaved. Because in the 100%, we saw that initial spark, right? So we wanted to see how 33% behave. And we got a very controversial result in the sense that it propagated completely to almost all the cells. So the interesting part in this was that after that initial cell went into thermal runaway, again, this is only at 33%. Even the trigger cell is at 33%. we found that, at a certain point, there was heavy smoke, electrolyte leakage. When the test was complete and we looked at the test setup, we found that there was a lot of electrolyte leakage. It was on the table, the test table, and I think that is what constituted to the heat spreading to the other cells and also for the heavier smoke that we observed. But of course, we didn't see any fire because these are only at 33% state of charge. And then we now going on to manufacturer C. This was a manufacturer that gave us actually 4 different types of materials. One is the mica sleeve that you see around the cells here. Another one was what we call a mica plate. And then we also got intercell separators from them, which I'll show you on the next page. And then we also got something called the mica blanket from them. But in this case, we used the mica plates and the cell sleeves, and we found that we had complete thermal runaway. In this particular case, we use the intercell separators and we use the mica blanket. Again, as you can see from the picture, we had a complete thermal runaway. And in the last case, we used the cell sleeve, we used the intercell separators, and also the mica plates on top and the bottom, and the flame barrier sheets on the top and the bottom, and also on the sides. And we found we had complete thermal runaway in this case also. And this is manufacturer D. This is again an intumescent type of material. And in this case, what they had done was given us 2 millimeter separators that went between the cells. And we also kept 2 millimeter plates of intumescent material all around on the top and the bottom. And as you can see from the picture here, they went into complete thermal runaway. The same company has provided us with 4 millimeter separators, and we are looking, as well as sheets that would go around, and we're looking at carrying out some tests with them. We did place the 4 millimeter separators between the cells, but they had complete propagation. We are planning to put them around the container also to see if that will help. Last one that I wanted to show you was a container. This is actually a container that we tested probably around the 2015, 2016 time frame. And this was in the beginning when we had the regulation coming out. And what we had done here was, this company has this type of pretty big suitcase type of configuration where they have a glass bead type of material that they place on the underside of the lid. And they also, can put other glass beads inside this box itself. But we went with the sacks that had the glass beads on the underside of the lid, and we carried out this test. And as you can see from the values of the open circuit voltage of these fully charged cells, only the cell that was triggered went into thermal runaway, and all the other cells did not go into thermal runaway. As soon as the cell goes into thermal runaway, the glass beads, actually the bag opens up and the glass beads fall on it and smother the cell that went into thermal runaway and prevents propagation of the thermal runaway. So one of the things we did was look at the material properties of these different materials that we studied, mainly A, B, C, and D. Manufacturers A, B, C, and D. And what was observed was that whenever the thermal conductivity was little high, as you see with manufacturer B, it does prevent propagation. The intumescent cell separators also had a little higher thermal conductivity, but from our results, we did not find that to be as effective as the B and C. And if you recall the designs, B was really a block mold type of design, whereas the manufacturer D was just plates that we placed, intercell separators were like plates that we placed in between the cells. So to summarize that part of the study, we did study materials from 5 different manufacturers, and I didn't mention the 5th one because we had actually a huge fire with their materials. So I didn't want to show it here because we're not going to learn anything from that. What we found was that only one material from one manufacturer actually prevented propagation. And even with this, in the beginning, we saw some small fire and sparks. And so we're trying to work with them to see if we can prevent that also. And the block mold seems to have a better efficacy. Even from our previous tests, we did find that that design works better than just having interlocking separators or sleeves. And as I mentioned, the thermal conductivity of the materials, shows that that is pretty important in preventing the propagation. And also wanted to, reiterate that we are looking at worst case conditions for all the protocols that we've used, all the variables we've used in our protocols. And so just wanted you to keep that in mind. But that is something that you would typically see when in use. You're not going to have a less than 30% state of charge when you're using a battery. So in many ways, these types of tests are very helpful in designing batteries more safely. And we are continuing to work with more manufacturers of materials in this particular area. So today, the next thing I was going to talk about was quantified cells and batteries. And the background on this is in 2015, we were doing some internally within UL, we were doing some R&D tests. And one of the team from the fire research, one of the team members from the fire research group had purchased a set of 18650 cells. And, they came to us to just verify if it was okay with respect to, charging and discharging, and what protocol we needed to use to charge and discharge the cell. And when I looked at the values and it said 5 amp hours, I was very suspicious because I knew that, 18650 cells were a maximum of 3.4 amp hours with the NMC type. Sometimes it could be the NCA too, cathodes. And so, I told them that I was doubtful whether these are good cells. And so we started looking into this. And then, of course, in the past 2 years, we've done a lot more on this. So just showing you what we had purchased in 2015. This is what they look like. And these are the cans. The yellow label is on the outside can, and you can see it's labeled 5000 milliamp hours. When we measured the height, we actually found that it was taller than 65 millimeters. And we opened up the can and found that there was another cell inside the can with the circuit board attached to it. And the cell, said that it was about 1300 milliamp hours. And when we tested the cell, we got only 600 milliamp hour capacity from the cell. And we did an overcharge test, and this circuit board actually prevents the cell from going into thermal runaway. So we took out the board and we tested it because 18650 cells are supposed to have current interrupt devices. And so under an overcharge condition, they should be safe. But what we found is that it expelled its contents, as you can see from the picture here. So, just summarizing what I just said, that we realized that this was not an original cell, but a counterfeit cell. So, our current study was done with 3 different manufacturers. And manufacturer A is an original cell. It was bought from a trusted source. Manufacturer B was bought online. And this had the same label as manufacturer A with the same capacity name also, capacity number also. And then manufacturer C, of course, was the same manufacturer name as the one that I just showed you from 2015. As you can see from the capacity checks, manufacturer A, obviously, when the rated capacity and our measured capacities were the same. With manufacturer B, we got only 1.8 amp hour capacity, even though they labeled their cell as 3.3 amp hours. And with manufacturer C, it was even worse, even though they labeled it as 5 amp hours, we got only 1.2 amp hours. And as you can see, we did overcharge and external short tests on them. So going into the overcharge test, I know this is manufacturer A. I'm going to play the video. what you'll see from this is that the CID actually activates, and even after 6 hours of holding it in an overcharge condition, nothing happens to it. It just, sits there with the CID, of course, popping open, but nothing, no other reaction to the cell. And if you look at the voltage and current profiles, when the CID opens, the current falls and the voltage hits the max of the equipment. And if we go into manufacturer B, which is the manufacturer that has the same label as manufacturer A, but was bought online, we first did an overcharge test with 1.8 amp hour current, 8 amp current, because we measured only 1.8 amp hours from it. So using that 1C rate, we did this overcharge test. And we see some smoke, but we see a lot of electrolyte leakage in this case. So going on to the next one, this is the same manufacturer B. Here what we did is, since they had labeled their cells as 3.3 amp hours, we took 3.3 amps as the charge current and carried out the test, and it is pretty interesting. So you see that it does go into a really big fire. So now going to manufacturer C. Here, we did the same thing. We took just 1.2 amp current because we measured only 1.2 amp hour capacity, and we did the overcharge test. And you can see that first the Kapton tape, starts peeling, then the shrink wrap or the label on the cell starts peeling. And then we see the cell actually expels its contents, and you can see the shrapnel here on the right side photos. So, and then we did the external short circuit. Of course, manufacturer A has a PTC in it, so we didn't see any catastrophic failures. The PTC gets activated, and we didn't see any high temperatures at all for the 3 hours that I'm showing only a little bit of the test here, but we held it for 3 hours, the short circuit for 3 hours. With manufacturer B, we did see that it expelled some of its contents under the short circuit study because it does not have a PTC. With manufacturer C, we found that it actually expels its contents like it did under the overcharge test. And you can see in both cases, we did record high temperatures. So looking at, this is just summarizing what I've told you, they are quite different in terms of what they have on their labels, the quantified cells, as well as what we actually measured. And this is just summarizing those values. Physically, they look alike. This just is just a different shade because of the way the picture was taken, but you can see that these two, A and B, look physically very much alike. It's not possible to look at a cell and tell whether it is a counterfeit cell or an original cell. And with manufacturer C, there was nothing to compare it with. But when we did a destructive analysis, what we found is manufacturer A, which is the original cell, has a central mandrel, and they also have plastic insulators on the top and bottom. With manufacturer B, we saw a plastic insulator. There was no metal mandrel in the middle, but it was quite flimsy. It wasn't like the one we saw on manufacturer A and in manufacturer A cell. And we also did not see a bottom insulator. With manufacturer C, even the construction looks pretty bad. The way it's rolled up, you can see it's crushed on the top. No metal mandrel, no insulator on the top or the bottom. So going into the parts inside the header, which is critical for these 18650 cells, you can see that with the manufacturer A, there's like a ton of parts which constitute insulators, the CID, the PTC, and so on. But with respect to manufacturer B, we don't see either PTC or a CID. We even saw some rust marks on the underside of the lid. Manufacturer C, again, does not have a PTC or a CID. We did some chemical analysis and we found that manufacturer A is nickel cobalt aluminum, which is what they tell it is. Manufacturer C was actually nickel and manganese with a low cobalt content. Probably, they were probably trying to do an NMC. And then with manufacturer C, it was only MnO4 cathode. So this is just summarizing everything. I've mentioned all of that. So I would, for the sake of time, I would like to, go to the summary page. So what I would like to say here is that, we do not know the difference by just looking at cells, whether they are from an original equipment manufacturer or if they're counterfeit, especially when the label and everything else looks the same. The model number, the way they label it, and the capacity and everything looks the same. So it is good for people to know, first of all, have a knowledge about the cell models and the relative capacities. So for instance, when it's labeled 5 amperes, you know that an 18650, at least, in today's times, does not have that much of, you cannot pack that much of a capacity. The manufacturers have moved on to larger sizes, cell sizes, to be able to accommodate more into their cells. And the physical and electrochemical characterization will provide further confirmation on the quality. And, we did find that there's a difference in the capacities when you measure them. And off-nominal tests also provide more information on whether these are real or counterfeit cells. And it's very easy once you do even just looking at the voltage curves, you can tell the difference between a cell that has a PTC and does not have a PTC. Destructive analysis and SEM-EDS are also required to physically know the difference in, construction, and also provide analysis on the morphology of the different components as well as the chemical composition, that if you want to know, whether these are really authentic or not. And other factors to watch out are undeclared shipments and inexpensive cells that can be procured online with a fast turnaround time. Those are all red flags that you might have received a counterfeit type of cell. So I'd like to thank my collaborators, NASA Johnson Space Center, where we did a lot of our studies and we are still continuing to work with Derek and James for spectroscopic analysis, and of course my team at UL. And just a quick message to the students. My 2 P's will be passion and perseverance. And now I guess I'll turn it back to Susmita